Good morning, everyone. So we're going to jump back into chapter 5 here. We're kind of in the start of the calorimetry section. I'm trying to look at heat changes that are going to take place. Here we're looking at a problem where we have a hot piece of iron. It's at 100 degrees. So we have water in some sort of container that's at 25.0 degrees. We're going to put a hot piece of iron into this container that's heated up to about 100 degrees C. And so the piece of iron is going to lower in temperature, and then the water is going to increase in temperature until they equilibrate and have the same temperature. We're told that that this is in an isolated system. That's really just so that we don't have any heat exchange taking place between the container and the surroundings. So the only heat exchange is between the iron and the water, is why that's being told to us. And so we could sort of relate the heat change of iron versus the heat change of water, and we just have the idea that iron's dropping in heat, water's increasing in heat, so we can put a minus sign in front of one of them to imply that their heats are opposite of each other, but equal in magnitude. And so for iron, we would have the heats equal to the MCS delta T, the mass of iron, the specific heat of iron, times the temperature change for iron, and that would equal the MCS delta T, the mass of water, CS of water, temperature change for water. So if we start filling in some of our data here, we'd have 10 grams for iron. Now, it says to use the values from the book. In the previous slide in the notes, I'm just looking at it on my laptop here. It says the CS, the specific heat of iron solid, is 0.45 joules per gram Kelvin. And so this is just from the previous slide. And then I'm going to write TF minus the initial temperature. So the final temperature, TF, is our delta. So our delta T would be the final temperature minus the initial temperature. And so the initial temperature for iron was 100.0 degrees C. And that's going to equal, plugging this in for water, keeping our minus sign here. And again, we're not putting the minus in front of water because the heat change of water is negative. Actually, water is increasing heat, but that is just the opposite of the sign of the heat change of iron. So minus 100.0 grams. That's 4.18 joules per gram Kelvin from the previous slide. So we're pulling that off the previous slide. And then our TF minus TI for water is TF minus 25.0, because water is initially at 25.0 degrees C. Now, I'm going to leave my temperatures in degrees C, and I'm not going to worry about the Kelvin, right? Because a delta T, we were talking about this before, a delta T in degrees C is going to equal the same magnitude of a delta T in Kelvin. So I'm not going to worry about this right now. That's actually okay. Again, think about if your delta T was 1 Kelvin, that's a 1 degree C delta T. So 298 to 299 Kelvin is 25 to 26 degrees C. So in delta T's, degree C and Kelvin are equal in magnitude. Okay, and so at this point here, like we could sort of, I was starting to look at the answers last time, trying to see if I can eliminate any answers. There's actually two really easy answers on this multiple choice test that we can eliminate. It's A and C. Because why would water's temperature drop? Like, we're putting something hot into water. The water temperature dropping really makes no sense at all. So if we're being wise, we might want to, roll out answer A and C. And if we do that, that might help us. If we were to mistakenly come up with those answers, like if we miss a minus sign, we might come up with one of those as our answer. If we rule those out right off the bat, we can probably save ourselves from putting the wrong answer in. And then I was also looking at 32.5 as probably being too high of a temperature change, just from the thought of 10 grams of only 0.45 specific heat. That iron doesn't have that much heat to lose to water because of its relatively low specific heat. And water has a relatively high specific heat. It takes a lot of heat for water to absorb to increase its temperature. So I was kind of thinking that 32.5 is probably going to be out of reach. Now at this point we have a relatively, well, depending on your algebra skills, an easy or hard algebra problem to solve. We just have to do some multiplying, some factoring, and then the same thing here. We have to do some multiplying, some factoring, and then some rearranging. Okay? So if you want to, maybe take a minute or two to try to start that factoring process. In about a minute, I'll just start writing out my work if you want to follow along if you get stuck. But it really just becomes kind of an algebraic problem at this point, is trying to solve for TF. But the other detail is that both the iron and the water have the same final temperature. So they're both going to end at the same TF. So the TF for iron, the TF for water is the same final temperature. So try to start the math. I'll give you a minute or two, and then I'll start trying to solve it too. All right, so if we take a look here, so we did the 10 times the 0.45 times TF, and then 10 times 0.45 times minus 100. So I got 4.5 TF, and then minus 450 degrees C equals minus 418. So 100 times 4.18, keeping the minus sign, so minus 418 times TF. And then minus 100 times 4.18 times minus 25 gives me plus 10,450. So getting these signs right here are really helpful towards getting at the right answer. So then I was adding 450 to both sides. And so I got 10,900 degrees C. Then I added 418 times TF to both sides. So 4.5 plus 418, 422.5. And then just solving for TF. And so relatively long problem. I mean, if we have to solve a problem like this, maybe, we're making sure this is one of the last problems on the test we have to do, or that we go find other easier questions to do first. We don't want to not see a question on a test because it takes us 5 or 10 minutes to work the algebra out on a problem. Not that it necessarily takes that long, but that's the process on this one here. We solve for TF, works out to be 25.80 degrees C. Now, again, if the Kelvin gets confusing, what you would have to do is convert your initial temperatures to Kelvin, and then convert the final temperatures would come out in Kelvin, and then we just have to convert those back to degrees C. What we don't want to do is we never would want to take a specific heat and multiply it by the degree C to Kelvin temperature conversion, which sometimes I've seen is, sometimes we say, well, 1 Kelvin is, negative 273.15 Kelvin or whatever it would be, and then do some weird conversion. We don't have to do that conversion on our specific heats. So another way we could write this is we could write 4.18 joules per gram degrees C, that would be synonymous with 4.18 joules per gram Kelvin. And then we could just use whatever unit we need to use in a problem if we're going to get caught up on this. Okay, so again, when we're talking delta T's, degrees C, Kelvin are the same unit, or synonymous in numerical value. Okay, so one of the forms of calorimetry is instead of putting a hot piece of iron into a container, what if we do a chemical reaction inside of a solution and we track the temperature of that solution? And that's basically what we call coffee cup calorimetry, is just a way of trying to measure the temperature change with a thermometer of the solution, and then relating that solution's heat, the heat change that the solution undergoes, to the reaction that led it to undergo that temperature change. And so in this form of calorimetry, and really in all forms of calorimetry, we're trying to relate the heat change for some reaction that's taking place to the surroundings of the reaction. We know this basic idea that the heat of a reaction is always the opposite of the heat change of the surroundings, and the surroundings of this reaction here is the solution that it's taking place in. And so then we can have the Q reaction in this situation here is a negative Q of the solution. And then the solution is mostly water. I mean, it doesn't have to be water, but the examples we tend to use is that, that the solution is mostly water. So you often see that the Q reaction is equal, or maybe approximately equal to, just the negative M solution CS of the solvent, and then the delta T of the solution. It's like an MCS delta T that we previously saw, where we're just using now the mass of the entire solution, not just the solvent, but then we use the specific heat of the solvent, which is an approximation, but it's a pretty good one because mostly we're dealing with the solutions taking place in water, and then the temperature change of this solution that we're tracking. And then the key is that the solution is the surroundings of the reaction, not the reaction itself. So sometimes that's a little confusing. We'll have a reaction take place in water. We're tracking the temperature change of whatever that entire solution is, so we're tracking the temperature of the surroundings. I previously mentioned last time, if you recall, can't really put a thermometer on a reaction. That's a little tricky to do because a reaction is just something that was there or something that's not there anymore and something new is formed. Hard to put a thermometer on that. It's much easier to put a thermometer on the things that reaction's in contact with. That would be the surroundings. So let's take a look at a problem that's common for this type of calorimetry. So here we're told that we have ammonium nitrite given molar mass. So ammonium nitrite's added to water inside of one of these calorimeters. If 2 grams of NH4NO2 leads 50 grams of water, initially at 25 degrees C, to lower in temperature to 22.24 degrees C, then what's the enthalpy of solution as like a property of the ammonium nitrite in units of kJs per mole? And then we're told to assume the CS of the solution is that of water, which is 4.184 joules per gram Kelvin. and then the heat capacity of the calorimeter. This term here is something you sometimes see. This relates to the way the lab gives you this information. This is just the definition of an isolated container that's not losing any heat or gaining any heat from the surroundings. I'll let lab handle when this isn't zero. So the lab maybe talks about how you could add in the heat of the calorimeter, adding some heat if you can absorb heat from the surroundings or give heat to the surroundings. But for lecture examples, we're always assuming that the reaction's taking place in an insulated environment. That is just the previous equation. That allows us to write that the heat of the reaction is just a negative the heat change of the solution, and then that would be negative M solution CS of what we're told here of the solvent, and then the delta T of the solution. And so then from first glance, is this exothermic or endothermic? Is for the compound dissolving in water, is that reaction? And you can think of the reaction itself. The reaction would be NH4NO2, which we should know is water soluble. Anything containing ammonium is water soluble. So we take this compound here, place it into water, and then it should dissociate into ammonium and nitride ion. So this is the reaction that's taking place. So this is the chemical reaction that's occurring. Do you think that reaction is exothermic? Does it release heat? Or is it endothermic and it absorbs heat? So if we can think of the sign of this reaction from the information that's already been given to us, then we're halfway towards choosing the right answer or being able to guess the right answer. So the temperature of the solution is dropping. So remember how at the start of class or on Wednesday we passed around a couple of bags. One was we put calcium chloride into water. That made the temperature go up in the water. And then we added, it was ammonium nitrate, but we added ammonium nitrate and that made the temperature drop. And the temperature was dropping because the reaction was absorbing heat. And absorbing heat is an endothermic reaction. So the reaction's absorbing heat, it's increasing in its heat, but it's doing so by taking the surroundings heat. And so this should be an endothermic reaction. Based on the information provided in the problem, that means the delta H should be greater than 0 for the solution of the compound in water. And so now that should be the proper sign that we get when we apply the math here too, but if we have a double check on knowing what the sign should be, that should help us, making sure that we make a mistake, maybe we can catch it. And so our Q reaction, we just go negative, and by Q reaction, I mean the reaction occurring inside of this particular calorimeter. So the reaction being the 2 grams of compound that's reacting inside this calorimeter. The mass of the solution is the 2 grams plus the 50 grams. So it's the mass of the entire solution. So mass of the water and the compound added together. So that would be 52.0 grams if we're tracking sig figs, which I don't know if I care so much to talk about sig figs in every problem. Actually, the previous example would be really delightful to go through the sig figs in, so we'll skip that on the previous example. But it was 50.0 plus 2.00, so that'd be 52.0 grams for our solution. CS here is 4.184 joules per gram Kelvin. And I'll just write that joules per gram degree C. And then TF minus TI. So as long as we get finalized the initial, and as long as we understand that this minus sign is coming from reaction negative of the surroundings being the solution, then we should get the right sign out here. So the final temperature is 22.24, and then minus 25.00. So let's do that math. So I get plus 600, and that's joules. How do I know it's joules? I'm going to write 600.5 joules. And then I know it's joules because that's my unit here. I had joules per gram degree C. My grams canceled. My degree C canceled, and my delta T. So my delta T units cancel here into joules per gram degree C, and the only unit left is joules. Now, we see an answer 600 kJs per mole. Maybe we're looking at this answer here and thinking, okay, maybe that's the right answer. Is that the right answer? Probably not, because one, this is joules. I don't even know where the per mole is. We need to think about where the per mole's coming into play. But that's not even the right unit. So we have to be a little careful. We have one more step to do. The problem's looking for the heat per mole of the compound. We just did 2 grams. So if we wanted to get the numerical answer out in this problem per mole, we would have needed to have probably a much bigger calorimeter. We would have needed to have more water. We would have needed to be able to add an entire mole of ammonium nitrate, which would be 64.05 grams. We've only added 2 grams. And so if I want the heat of solution in the unit kJs per mole, I just have to relate my Q reaction here that we got out plus 600 joules and just relate that per mole. And so the way I could get my delta H would be to take the 600.5 joule value, and let's just divide, let's take that heat per ratio of whatever the limiting reactant was in the reaction that we were carrying out, which was only one reactant, ammonium nitrate, or ammonium nitrite. So we're going to divide by 2.00 grams, and this step here is almost always going to be whatever the limiting reactant was. So if we had a reaction taking place, we would just want to figure out, if there were 2 things reacting together in our calorimeter, we would just want to find out which of the 2 was a limiting reactant. The heat change is the heat formed per quantity the reaction was actually taking place. So 2 grams, and then we just go grams to mole. 64.05 grams per mole of the compound. We could have also just taken 2 grams, converted it to moles, and then divided joules per moles to get kJs per mole too. So you could, if that makes it simpler, we could have just said, well, 2 grams of ammonium nitrite, how many moles is that? And just go joules per mole to get the unit to come out. We can just look at the units and be like, well, I got to divide by moles here. And so we're just doing that through dimensional analysis in the problem. So we go 600 divide by 2 times 64.05. And then, again, that's in joules. We just need to do one final step, 1,000 joules to a kilojoule to go to kJs per mole. Okay, so, whoops, not that canceled. The joule cancels, the gram cancels, and we're left with kJs per mole, and numerically 19.2. So I prefer when they give multiple choice in these questions, not data entry, because it really forces us to think about the sign. It really forces us to make sure that we're getting the plus from the reaction losing heat, the solution losing heat as it takes place. It's because the reaction absorbed the heat. The reaction took the heat because it was endothermic. Now, we need an exothermic reaction to release heat for the solution to go up in temperature.
Why do you cancel degrees Celsius when it's 6 degrees Kelvin? Like you put degrees Celsius on the bottom of the joules per.
Yeah, so that's coming back to, like, again, we're multiplying this by the delta T, so the change in temperature. So I could have done one of 2 things. I could have either converted both the 22.24 and the 25 to Kelvin and then taken the delta. But if we do that, it's going to be the same delta if we just left it in degree C. And so for that reason, we can go joules per gram degree C or joules per gram Kelvin. Yeah, and so like 4.184 could be joules per gram Kelvin or degree C. So again, a delta T in degree C equals a delta T in Kelvin. Okay, so we have one other form of calorimetry, and that'll also make us think about heat of the reaction versus the heat of the reaction taking place. So bomb calorimetry is a constant volume form of calorimetry. Here we have a vessel that, I should have brought this, I usually bring it, I just totally forgot this morning, but it's a stainless steel container that's really thick stainless steel, pretty heavy. It ends up being, for a pretty small container, probably about like 15 or 20 pounds, just from the amount of stainless steel that you're going to want to have to be able to handle the combustion reaction that's going to take place inside of that calorimeter. And then you also charge that calorimeter with like 25 times atmospheric pressure of oxygen. So you have a really high oxygen environment inside this calorimeter. So we fill the cell here up with O2. You try to get as pure oxygen as you can. You actually flush it out to get rid of residual nitrogen from the air. And then you could have lead wires leading to a sample inside that container that you prepare, and then you can detonate that sample. It really just ignites it. I don't think it goes kaput exactly immediately. It actually catches on fire and kind of burns over a few seconds. And so the reaction takes place, and this reaction here is always going to be exothermic. I mean, just the nature of the type of reaction that's going to take place is something that ignites, you know. So this is going to be a case where the calorimeter gets hot, and then the heat's going to go into the water bath that's surrounding the vessel. So we just have a water bath to take the heat off of that cell, so we can put a thermometer into the water bath, and then the water bath becomes the surroundings. So here, just like before, we have a Q reaction. What's the heat change of the reaction taking place inside that container? Well, it's the negative the heat change of its surroundings. And here the surroundings is the entire calorimeter, where the QCal is calorimeter. And so you'd have to standardize the calorimeter. You'd have to do basically some test runs with a compound that you know how much heat it gives off, and maybe do 5, 10 trials, or as many as it takes to kind of keep getting a similar answer for that heat capacity of the calorimeter. It's basically from the change of the temperature of the calorimeter, what's the heat associated with that temperature change. And so the calorimeter is usually just described as an object as opposed to being a specific substance like water. And so for an object, where you have a lot of different substances, right? We have the container itself, we have these materials, like how much stainless steel and its absorbing heat will impact the temperature change of water. You have the water itself, you have a stir motor, you have a thermometer, you have a lot of different things in here that are important for this type of calorimeter, not just the water itself. And so we're thinking of this calorimeter as being an object, not just one pure substance, even though it's mostly water, but there's a lot of other things other than water. And then it's also materials that you reuse. Like a coffee cup calorimeter, you recycle or use a new coffee cup, you know, with most of your trials. Or maybe every other student comes in and uses a different coffee cup. Here, and we actually do this experiment in my physical chemistry lab course that chem majors take, and we use the same calorimeters. I mean, maybe every couple of years we buy new ones, but I mean, we reuse these year after year. And so based on that, you get one heat capacity of the calorimeter, ends up looking like this. Our Q reaction, I don't know why Q is my hardest letter to write, but Q reaction is the negative Q of the calorimeter, and the Q of the calorimeter is a CCal. Instead of a CS, it's just the heat capacity of the calorimeter, and then times a delta T. And this unit here will just have units, often kJs per Kelvin, with no mass unit. So you see no MCS delta T here like we saw previously, but just a CCal times a delta T. So you see no gram unit here, just kJs per Kelvin, because again, we have the entire object. It's the calorimeter, how much heat does it raise per degree C of temperature change? How much heat is absorbing per degree C or Kelvin increase in temperature? And again, the minus sign's still just like before because this is the surroundings of the reaction. So we have that Q reaction negative Q of the surroundings. And so let's look at an example just to see this in action. As long as we understand the bomb calorimetry problems are usually a little bit easier because we don't have that mass term to worry about. But we just have to know that we don't have the mass term to worry about. So here we're told that we took a 1.50 gram sample of heptane, and it's combusted in a bomb calorimeter with excess oxygen. If the calorimeter has a heat capacity, that's the CCal, of 10.94 kJs per Kelvin, including the water that surrounds the cell, what is in the calorimeter increases in temperature from 20.000 to 26.589 degrees C. So we're going up in temperature for the calorimeter for the surroundings. What is the enthalpy of combustion of this compound? Also units kJs per mole. Now, delta H should be exothermic for the compound. Unfortunately, all the choices are exothermic. So on this particular problem, knowing that wouldn't have allowed us to narrow in on any of the answers. But that's just this particular question. So maybe different questions on different exams or quizzes will give you different choices where knowing it's exothermic would help you narrow in on the answer. The reaction taking place inside the calorimeter would be the C7H16 plus O2 forming CO2 and water. And we don't necessarily have to balance this reaction, but it's the reaction that's taking place inside the calorimeter, just so we know that we're getting this combustion reaction taking place, and that's kind of how we're connecting to the idea that this has to be exothermic. Okay, and so that's the reaction taking place inside the calorimeter. Now, how do we solve the problem numerically? Well, we come back to Q reaction. Negative heat capacity of the calorimeter times delta T. So that'll be negative 10.94. Now, one of the easiest ways to go wrong in problems is to not write units in. And I know that's probably most students just don't like to write units. Write units, they help us, because if we write the units in, we're not going to then wonder, well, where's the mass? Do I need to multiply by 1.500 grams here? And we don't need to multiply by the mass of the sample. We don't even know how much mass of water there is, so we don't even really know the mass of our solution anyways. But here we see no mass unit, so we're just multiplying by the temperature change. And so final 26.589 minus 20.000 initially. So our delta T would be 6.589 degrees C. And again, that'll cancel into the Kelvin. So we go 10.94 times 6.589 gives me negative 72.08. Now we're already in kJs at least. From the problem, we had kJs per Kelvin multiplied by 6.589 degrees C. So the delta T was positive. And again, I'm just making sure we see that unit cancels. That's okay. Degree C in Kelvin. We could have also before just written this as degree C if we wanted to anyways. We could have just changed it to 10.94 kJs per degree C. Would also be okay. And so we get 72.08 kJs. And again here, this would be for the reaction occurring inside the calorimeter, not for the entire mole of the compound reacting. So to go to kJs per mole, we want to divide by either the mass or the moles of the limiting reactant. So we're even told here that oxygen's in excess. It would be crazy to not have oxygen in excess. That's the whole point of this type of example, is to have a really high oxygen environment. So we definitely have plenty of oxygen. So 1.500 grams of C7H16 to go heat per quantity of the limiting reactant. We could have also, again, just converted that to moles and divided by moles here, or we can convert to moles through dimensional analysis. So we have 100.21 grams per mole. So that's what's being conveyed to us here. So again, we keep our minus sign. So still exothermic, I get minus 4815, or call it 4816 kJs per mole. So these types of problems are where we come up with ways in the lab of determining delta H's of reaction. Now, I previously thought we could, like if you imagine doing a combustion reaction starting with graphite being the elemental form of carbon, and then you're forming only CO2 there in this exact environment, then this reaction would be telling you the enthalpy of sort of like the formation. It's going to be a topic we talk about in a minute. It's going to talk about the enthalpy it takes to form CO2. We can imagine doing this with H2 in the calorimeter to figure out the enthalpy it takes to form water from its elements as well. And so if we get into a spot where, or in a moment where we start to tabulate or know delta HF values, if you know the delta HF, the formation enthalpy of CO2, if you know the formation enthalpy of water, you can use these experiments here to determine the formation enthalpy. Hitting some weird button on here. Then we can use that to determine the formation enthalpy on like a compound like C7H16. So when we get into the topic of formation enthalpies and where they come from, they're coming from experiments just like this. So it helps us start to see where tabulated data we might be looking up in the back of our textbooks is coming from, the type of experiments that furnish that data. Okay, so quick summary so far is exothermic versus endothermic reactions. So exothermic reactions release heat. The heat's released into the solution, so it goes up in temperature. That's what's going on in the previous example. So we had the exothermic combustion reaction, making the cell hot that is taking place in. The hot water goes into the water that surrounds it, and its temperature goes up. Endothermic reactions do the opposite. They absorb heat from the surroundings, so the surroundings heat is dropping, the temperature of the surroundings drops. So the temperature of the surroundings, the exothermic reaction is increasing. We have this basic relationship, heat change of the reactions, the opposite of the surroundings, opposite of the sign of the surroundings. Now, our delta H for an open system, delta H is equal to QP. QP is just for the open system. It's just the heat change of a reaction occurring in an open container. And so we saw that was the example of our coffee cup calorimeter. It's an open container, insulated though, so we don't have heat exchanging with the surroundings. We design it that way just to make the math simpler. And so our Q reaction, negative Q solution, negative MCS delta T. And then for our closed system, now we didn't actually talk about this on the previous slide, but if you think about the container being a closed volume system, there actually is a small amount of work change that can be going on during the course of that reaction that we're ignoring. And so we have the delta H is, if I zoom in here, you can see it's approximately equal to the heat change at constant volume. So if you were thinking back in the bomb calorimeter example, well, doesn't the fact that it's not at constant pressure factor in? And it does, but we just ignored it. And so it's a really strange thing in this chapter, in my opinion, that we spent a lot of time talking about work and what it is and how to quantify it. And then we get to a problem where there actually can be a change in work based on the type of reaction occurring inside the calorimeter. We could calculate it, and it's actually very small. And so we ignore it because it's a very small correction. So unless, and I think this to me makes a lot of sense, that unless you're powering a piston or moving an object with the reaction, the amount of work is going to be pretty negligible. So might as well just ignore it. And so that's why we say delta H is approximately equal to the heat change at constant volume. That allowed us to go Q reaction, negative Q calorimeter, C cal times delta T. The key being at the end of the problem, though, for both forms of calorimetry, we have to relate the heat change to the actual quantity being asked in the problem. We're almost always going to ask you for a property of the compound from the data in the problem being a smaller reaction, So usually we're not taking an entire mole. So if we want to get kJs per mole, we have to do that conversion, heat change per limiting reactant of that reaction. Okay, so let's move off of calorimetry into Hess's law. Now, Hess's law to me is actually pretty simple. This is the idea that if you know A goes to B, let's say the delta H here is plus 10 kJs, is just for some generic reaction, then you know B goes to C is, let's say, negative 20. So we know B goes to C, that's negative 20. Well, because of the first law of thermodynamics, A goes to B, went up to here, so it goes upward by 10. And then when we come back down to C, we go down by 20. So B to C goes down minus 20. Trying to draw this somewhat to scale, so that we can then know that if we were to add these reactions up for A goes to C either directly or through B, that doesn't make any difference, that the difference between A to C, would just be the sum of these two delta H's. So if you imagine adding these reactions up, you'd have A plus B goes to C plus B, and then B would cancel. So wherever the energy is of B would cancel out the energy of B on the reactant side. And so you just have A goes to C being plus 10 minus 20. So delta H being minus 10 kilojoules. So now this is the idea of path independence, because it doesn't matter how we get to C. What this is telling us is if we go from A to B to C, that we went up by 10, then down by 20, net down by 10. And then if we just go from A directly to C, if we have some other way of carrying out this reaction where we say, well, we're going to bypass B altogether, we're just going to go directly to C, what about that reaction? It should have exactly the same delta H. And so this is all about path independence. So it doesn't matter what path we take. And then a path independent function is a state function. So delta H is a state function. Delta E is a state function. The ones that aren't are specifically Q and W, but in the context of like a mechanical system. So it depends on a mechanical system how you're carrying it out, how much heat and work you can get out of a reaction. Okay, so let's look at a problem like this. So like a Hess's law problem, what it tends to do is it asks us to find the delta H for some unknown reaction using the delta H's of other reactions where we have to piece together a puzzle. Where we have to piece together how do we take these three reactions and manipulate them in such a way that they add up to the desired reaction. So I have to somehow take all these reactions here and add them together, but I usually have to make modifications to add them up. Like if you notice right now, if I add these three reactions, I don't think it would make a lot of sense. If I just physically add the reactions as is, I would have NO plus 2O3 plus O2 go to NO2 plus O2 plus another 3 halves O2 plus 2O. See how nothing really balances. So we have to somehow get these reactions to balance out to give us this desired reaction up here. So how might we approach this problem? Well, what I would probably start to look for is, well, where are some of the reactants and products? So if you notice the first reaction has the NO2 and the NO, and it's actually kind of in the right direction and in the right quantity. So if I take that first reaction, and I'm going to leave off all of the gas, everything's gas here, so I'm just going to ignore writing the physical states here just for the sake of sloppiness or avoiding sloppiness. So I'm going to write NO plus O3 goes to NO2 plus O2, just writing that first reaction as is, and then thinking of what the delta H is exactly what it was in the problem, minus 198.9. These are all going to be in kJs. And so then the other two reactions must be used to get the O into the proper place and then to balance out or to remove some other type of intermediate from the problem. Like if you notice, there's no O3 in the overall desired reaction we're trying to add up to. Let's even make sure that we see that the target here is adding these up to get NO plus O goes to NO2. And so now only one of the reactions has an O, and that's the third reaction. So I'm looking here. That's the only place I see a reaction that has an O atom in it is the third reaction. So why don't I use that reaction next? If I flip that reaction and I go 2O goes to O2, now I flip the reaction because I want to get the O onto the reactant side, because the O is down here. Not on the product side, it's on the reactant side. But then there's only one O, not two O's. So I need to cut these coefficients in half. And so now what happens to the delta H when we do that? So if I flip the reaction, I got to flip the sign. And if I cut the coefficients in half, I need to multiply by half. So the delta H of the reaction, once I flip and cut the coefficients in half, should be plus 142.3 divided by 2. In fact, why don't I just write it this way here? Why don't I write minus 142.3 and then negative a half out in front. Does the guy flip the reaction? Oh, yeah, thank you. 495. Yeah, I was looking at the middle one, and I was flipping the third reaction. Yeah, good catch, thank you. And so then what about the middle reaction? Well, that's going to help us get rid of ozone here, because ozone's not in the overall balance reaction. Right now, O2 is in the balance reaction. If we add these two reactions up, we have O2 and O3 still in the reaction. That's where the middle reaction comes into play. And so I'm going to want to flip that reaction as well, because I want the 3/2 O2 over here to cancel out with the 3/2 O2 that's on the product side right now. And then I want the O3 to be on the product side so it cancels out with the O3 on the reactant side. So if we have O3 on the reactant side and it's not in the reaction, then I need an O3 on the product side. And so then I've flipped the middle reaction. So it'd be minus 142.3. Now, if you get good at these problems, you might be able to do the manipulations without writing out the reactions. But the first time or two you do these types of problems, I would be meticulous about writing out the reactions so that we really see how the reactions add up. And so the O3 is canceling, and then my 3/2 O2 is canceling with the 3/2 O2. And then we're left behind with the net NO plus O goes to NO2. So then the delta H's that I add up are these ones here, the manipulated delta H's. So we're adding the reactions up, so we add up the delta H's. So we'd go minus 198.9 plus, and I'm just like meticulous. I just go minus 0.5 times 495, and then I do plus -1 times -142.3. And we could be like, we could cross these out and know that that would be plus, but sometimes I'm just like, I'm just going to be a machine and plug this in and try to do this number plus the next number, and just being careful not to mess the signs up. So I don't know if anybody was doing along with me, but I was getting minus 304.1 or minus 304. I'm going to do it one more time. Yep, so I get it second time. Okay, so Hessel to me is a puzzle. So we're just trying to solve a puzzle for how do we rearrange or manipulate these reactions so that they add up to some new desired reaction. So if we're trying to find the delta H of a reaction, we could study it by calorimetry. We have two different forms, or we could use this approach if we knew some other reactions, delta H's, and then we could manipulate them. And then one of the last topics in the chapter is these enthalpies of formation that I was talking about or alluding to on the calorimetry topic. So if we imagine, this is kind of the idea that if you could do a calorimetry experiment on graphite where you combust it with oxygen to form CO2, and then the delta H of the reaction tells you an important property. It's like the formation enthalpy. So delta HF, that little F sign, is what we call a formation enthalpy. So here we're forming a compound. And so if you think of the reaction that forms 1 mole of the compound, then the delta H of that reaction defines the delta HF of CO2. And so this reaction here, the delta H of this reaction would equal the delta HF of CO2, but in kJs per mole. So to be fair, like you could have, if you want to write a formation reaction, like you're forming a compound, but then you want to start with its elements in their most stable form at room temperature. And we'll talk, like the next slide will list some of these stable forms if we're not sure what they are, but for carbon it's graphite, and so that plus O2 goes to CO2. And so the formation reaction there tells us an important property for CO2. For hydrogen, it would be H2 plus a half O2 goes to H2O. Now this is a reaction where it's actually perfectly fine to balance what we call the formation reaction with fractions as coefficients. So we have half a mole of O2, a whole mole of H2 to make a mole of water. So we just want 1 mole of the compound on the product side, and then we'll leave whatever fractions it takes to prepare them. So O2 is the atomic form or the elemental form of oxygen. So these are the most stable forms of these elements at room temperature. So just whatever at 298 K predominates for these elements are the physical states that we would form those compounds from. So water's delta HF is this number here. These aren't worth memorizing. But then if you have water liquid, it should have a different delta HF. Remember how phases matter. And so if we have a different phase from gas versus liquid for water, it would have a different delta HF associated with it. And so then, well, what if we form O2 gas? The formation of an element would be the identity reaction from itself. So O2 to O2, I think you can see here that if you have the formation of an elemental form, the most stable form of an element would be defined to have a delta HF of 0. And so the next slide outlines what some different phases and forms are for some different elements, so we can know what those are. So O2's delta HF by definition, because it's the most stable form of oxygen, would be 0. O3 is one of those allotropes. It's a different form of oxygen, presumably higher energy. We can see that it has a positive delta HF, meaning it takes energy to form it, and this is forming from O2. And so if we needed to balance the reaction, we're just trying to get the right number of 3 O's on both sides, so 3 halves O2. In fact, this was the reaction on the previous slide that we were looking at. So 3 halves O2 to O3. Now this is just showing us that ozone is higher in enthalpy. Being higher in enthalpy is like less stable, so being lower in enthalpy was more stable. So that's why O2 predominates as a more stable form of oxygen at room temperature. If we wanted to write this reaction for methane, how would we write this reaction here? Well, it would be carbon in its most stable form, solid graphite, and then plus 2H2 gas. And it has some negligible value. Now, the sign of a delta, like sometimes the sign makes sense. Like when it's O2 versus O3, we can relate that being positive makes sense because that's why ozone's less stable. But then some compounds will have a positive delta HF, other compounds will have a negative delta HF. There's not a lot of meaning associated with random compound sign of the delta H's. Usually they're negative, meaning that there's some reason why they exist as that compound and not elements. Now, so what states are like noted to be 0 by definition? So we have our gaseous elements, and a lot of those are diatomic molecules like H2, N2, O2, F2 and Cl2 in the halogen group also form diatomic molecules. We have all of our atomic noble gases existing as just a single atom. So those are our gases. These substances here in their gas phase would all have a delta HF of 0. We have 2 liquid elements, Br2 liquid, Hg liquid. Those would have delta HFs of 0 by definition. And then our metallic elements that are all the others that are solids. So we have our sodium metal, calcium metal, iron metal. So those sodium solid, calcium solid, etc. Carbon solid, graphite's a solid. Phosphorus, we tend not to ask too much about phosphorus and sulfur, but they are also solids at room temperature. I2 is also a solid. And so these would all have delta HFs of 0. And so then let's just try to make sure we see, some examples of things that are not 0, some things that are not the most stable form of these elements. Hydrogen atom, it would take energy to break the bond between 2 H's, so that would not be 0 and it should be positive. Same thing with O, it should take energy to break the O2 bond to make O atom. Carbon in some other form of, say, diamond would have a non-zero delta HF. Phosphorus, some other form, red, would not have a delta HF of 0. And then some other examples, like gaseous metals, for example, would not have a delta HF of 0. We're not going to get to the solution of this problem today, but where we're going to use delta HFs is final minus initial, where we can calculate the sum of the delta HFs of the products minus the sum of the delta HFs of the reactants. It's actually a very easy problem, but we'll show how it is that works out next time, and then do our final topic of bond enthalpies for chapter 5, and then we'll get into some chapter 6 topics on Wednesday. All right, guys, have a great day.